Ridiculous. Like it's one thing if someone's trying to like.
All right. What were the requirements for being aromatic? What were the requirements for being aromatic? Let's think about an even number.
Is it that or no? I forgot, man.
That's why we're going over it.
I thought, isn't that add this stuff up because
All right, well, think about benzene. You know benzene's aromatic, right?
Yeah.
Okay, so what does benzene have? It has all carbons are what hybridization? All those atoms in the ring are sp2. Okay, what else? It's planar. Okay, it has an odd number of pairs of pi electrons. Odd number of pairs. Yeah. All right, so look at this molecule up here. Is that molecule, do you think that molecule is aromatic? No. Okay, why? You got to give me a reason.
even number of pairs.
Okay, before you even get to the pairs.
Oh, okay.
What can you tell me about that carbon right there? It's not sp2 hybridized. Okay. Carbon is sp3, is not aromatic. Okay, what about this molecule? Ooh. Okay, what do you think about this carbon? What can you tell me about the hybridization? It's hybridized. Good. All carbons are hybridized. Okay. That was a safe answer, wasn't it? All right, but what hybridization is it? Do you remember? It's a carbocation. Oh my gosh. I'll give you a clue. Yes, it's sp2. Right? What is in the p orbital? Look, I'm going to draw the p orbital. Okay, so every carbon in that ring is sp2 hybridized. What's in this p orbital? An electron, an electron, an electron, an electron. What's there? It's empty. Okay, so the total number of electrons we have are 4. Okay, so what is that for even number or odd number? It's an even number. So what is that? Even number is not aromatic. Okay. All right. If you do, what is the 4n plus 2? There's a name for that. Huckel's rule. Yeah, like Huckleberry Hound. Huckel's rule. Isn't that his name, Huckleberry Hound?
Huckleberry Finn.
Oh, there is Huckleberry Finn too. Yeah, I was thinking of the little dog in the cartoon. Okay. Huckleberry Hound?
Yeah. No.
You've heard of Huckleberry Finn? It's Tom Sawyer, right?
Yeah.
Okay. I'm like, I'm not that old. Okay. You all still read those books in school. My girls do.
We were required to.
But now they're in their 20s. So okay. 4n plus 2 is the number of pi electrons. So what will you, if you were going to do Huckel's rule, 4n plus 2 would equal what for this compound? 4n plus 2 equals 4. Okay, so what's n? What's n? Okay, what's 4 minus 2? 2 divided by 4 is a half. Okay. Is that an integer? No. All right, how about this one? This one looks like Bart Simpson or his dad. What is it? Homer? What? Homer. Yeah, it looks like Homer, doesn't it? Okay, so what is the number of pi electrons in this? So what we're going to count is we're going to count everything that's in a p orbital. All right, so notice that we got 1, 2, 3, 4. Okay, thing is still off. Okay, what about this carbon? Well, if this carbon is sp2 hybridized, these 2 electrons are going to be in the p orbital. So they get to count. So it's going to be 4n plus 2 equals 6. Okay, so what's n? 1. Is that an integer? Yeah. How many pairs of pi electrons do I have? 6 divided by 2 is 3. Is that an odd number? This compound is aromatic. In fact, okay, that is how come this compound is unusually, that says unusually, it didn't want to write for me this morning, earlier either, acidic, because once it loses that proton and becomes the anion, it's aromatic, gives it that extra stability. So molecules that are aromatic are going to be unusually stable. Okay, they're going to try to be that way. Okay, I see another box. I may have that over there. Yeah. Okay, the pKa is 15, which is like unbelievable for a hydrocarbon. Okay, hydrocarbon. All right, with me so far? Is it all coming back to you? You slept since then. Okay, what is the shape of the benzene molecule? You can pick E if you want. No one's going to judge you.
Except
So while you're doing this, my husband and I are planning a trip to Orlando this fall because I can go anytime. Okay. They're opening Star Wars Galaxy Edge. I'm like,
I thought you said
this fall.
Oregon, and I was like, where did you going to Oregon?
No, Orlando. They're opening Star Wars Galaxy Edge, and they're opening this summer the new Harry Potter ride at Universal Studios. Hagrid's Myth. I'm like, y'all know that I'm going to buy a wand and do all of the tricks. I'm like, I can't wait. My daughter went with her 2 friends. They're all adult students. They all bought a wand, and they each of them, and they did all the tricks. Yeah, because you can wave your wand and stuff out. I'm like so excited. Doesn't that sound fun? I'm like, all right, good.
I know, right?
Okay, nobody picked the disc. Okay, what is the hybridization of each carbon in benzene? May the force be with you as you answer this question. We need a new movie. New Star Wars movie.
I probably need to make a new one.
I'm sure there's one in the works. They make too much money. Okay, was 17 my number? I don't know. You're all there. Yep, sp2. sp2. Okay, which of the molecules below is considered aromatic? Okay, one is not. Okay, this one is not. Okay, but this one is, and this one is. Okay. Okay, what do you think about these? Ooh. Taking another step up the ladder. Okay. At the top of the ladder is aromaticity habit. What do you think about that phenanthrene thing? Okay, first of all, is every carbon sp2 hybridized? Every one that's in the...
Yeah.
All right, what else? What else we need? Okay, so how many? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. There's 14 pi electrons. Here, I guess I should write the pi too. 14 pi electrons. Everybody agree? Okay. So what does it need to be? Is that aromatic or not?
Yes.
Why?
Because 14 divided by 2 is 7.
That was 2 explanation points. Fail me now. Okay, so we have 7 pairs of pi electrons. That's an odd number, so it's aromatic. If you did the Huckel's rule, just because it's fun, it's not like liking my little finger. 4n plus 2 equals what? 14. What's n? What? 3. Right? 14 minus 2 is 12. 12 divided by 4 is 3. Is that an integer? Yes. You can do it with the odd numbers, though. All right, so what do you think about this thing? This is a tropylium ion. Where did we talk about that? We mentioned that not too long ago. What?
What did we mention?
We mentioned it in when we discussed a different topic. Let's see if I can get it to right. It's not taking my finger. All right, so what do you think about that one? Do you think that's aromatic or not? Why?
It has 6 pi electrons by that. 3.
An odd number. Okay, the p orbital on the carbocation is empty. Okay, so we're counting 0 for that. 1, 2, 3, 4, 5, 6. 6 divided by 2 is 3. Odd number. This compound is aromatic. That's how come the benzylic carbocation rearranges to that in the mass spec, because it is forming a cation that is aromatic. Okay, super stable. And it's commonly referred to as the tropylium ion. Okay. All right, we had 2 aromatics there. All right, now let's throw something else in. What about a heteroate? Okay, so this first compound up here is perol. Okay, if you had, let's see what you remember, a regular compound that wasn't in a ring, that looked like this. Okay, what's the hybridization of the nitrogen? It's sp what? Well, how many sites of electron density are around the nitrogen? 1, 2, 3, 4. So this would be sp3 hybridized. Okay? The thing about heteroatoms is they will change their hybridization if it would make the molecule aromatic. There's no way that you can make that molecule aromatic. But so let's look at this one though. because it's a ring. All right. So if this were to become sp2 hybridized, what would be in the p orbital? The 2 electrons. So your total system is going to have how many electrons? 6. Is it aromatic?
Yes.
Yeah. Okay. It will become sp2 hybridized. So what you have to do to decide about those is you have to say, all right, if it becomes aromatic, if it becomes sp2 hybridized, will it make it aromatic? If it does, then guess what? It does. Okay? If it doesn't, it won't. Okay? So if we hybridize it and there was 8 electrons, for example, okay, then that would not be sp2 hybridized. It would stay sp3 because it doesn't give it any extra stability. That help? All right. Let's see what I got down here. 3 pairs, aromatic. Okay, what do you think about that one over there? So look at that nitrogen. Think about it. Okay, so if you look at this nitrogen, okay, what hybridization is it without even worrying about whether the thing is aromatic or not? It's sp what? It's sp2 because there's a double bond. Okay, so there is a p orbital on the nitrogen interacting with the p orbital next to it, making the double bond. Okay, what about these guys? Where are they? They are in an sp2 hybridized orbital. Okay, so here's your p orbital, top lobe, bottom lobe, and where's that sp2? It's sticking out over here. So are you going to count those 2 electrons when you try to decide? No, because they're not parallel. The whole thing is this parallel. So we get our donut above and our donut below, and we wish we had a Dunkin' Donuts. Okay? So we're going to, the N is sp2 hybridized as is. There is 1 electron in the p orbital. The lone pair is perpendicular to the pi system. It is in an sp2 orbital, sticking out over here. So we're not going to count it. Okay? So how many electrons do we have? 6, which is how many pairs? 3. So is this aromatic? Yes. Okay. You're going to deal with oxygen the same way. Okay, you'll deal with oxygen the same way. Okay. When you're dealing with heteroatoms, people kind of get goofed up with how many can you count. Okay, you're either going to count 1 or 2. You're never going to count more than that. Okay, so if you're adding 3, there's no way you can have 3 electrons that are all going to be 0. Okay, that are going to have that side-to-side overlap. You get the little donuts above and below, both of those, just like the regular benzenes. Okay, something is considered anti-aromatic. That means that it's less stable than an analogous cyclic compound with localized electrons. It is characterized by being instability. It is classified if it fulfills the first criterion, but not the second. So that means that we have sp2 hybridized atoms all the way around. We have conjugation, but we have an even number of pairs of pi electrons. Those compounds are actually called anti-aromatic. Okay, these are anti-aromatic. Okay, since we seem to have this little issue here, do you see which way those are going? Okay, which is most stable? Aromatic. Which is least stable? Anti-aromatic. This is just delocalized electron. Okay, just making sure. Okay, so look at this first compound up here. Okay, so how many pairs of pi electrons do I have? 2, and that is what? Even or odd? Even. Are you sure? Okay. Just checking. It's an even number. This compound is classified as anti-aromatic. Anti-aromatic. Okay, what about that other compound over there? We already talked about it. All I told you was it was not aromatic. I didn't tell you anything else. Notice how many pairs of pi electrons we have. We have an even number. That compound is also anti-aromatic. Okay. Do you have these in slides? Yeah. Okay. You can see them. Okie dokie. So these are anti-aromatic. So you see the difference. Okay. All right. So what do you think about this compound? I don't think I've shown this one before. Because you know you can have some on the test you haven't seen, so you got to be able to apply. I'm all choked up over it. Are we up there? 15. I think that's right. I should count one. Wow! That about covered it, didn't it? Okay. I'm going to circle the right answer. When I circle semi-autumn, no. Why is it C and not B? What can you tell me about that? Okay, so you gotta look careful. Look careful.
So would there be two?
Would there be what? You wouldn't count any because there's no p orbital.
What's the difference between non and anti?
Okay, that's why we're doing this question. Okay, this is non because it doesn't have the whole ring. Okay, this one was anti because every carbon was sp2 hybridized. Okay, that's kind of the clue. So, and it has an even number of pairs of pi. So there's a little bitty distinction in there. Okay, does everybody see that that has 2? That one had 3. I can see why people picked aromatic, but it's not because of that carbon. So make sure you look carefully. What do I have? Okay. Well, before we do that one, let's do a couple more. Okay, I'm going to make some up because I'm good at that. Why they pay me the big bucks. All right, so what about that one? What do you think about that one? You don't like it? It's hard to draw.
No, it's not.
Okay, so how are we going to count it out? Let's count it. Where are we going to get count our electrons? 1, 2, 3, 4, 5, 6, 7. What do we do with the nitrogen? You just count 1. Where are these? In an sp2 orbital. So they do not count. All right. So we have 8 pi electrons, which is an even number of pairs. 4. So what does this classify? Anti-aromatic. Help? Okay. What about this compound? Let's throw oxygen in there. And just to remind you, I'm going to put those lone pairs out there. Okay, so what do you think about that one? Well, let's count the easy ones. Okay, now we think about that old. If I had a compound that looked like this, that wasn't the ring. Okay, what is the hybridization of that O in this compound? SP who? Because there's 4 sites of electron density, right? Each lone pair counts as the site of electron density. And you got electron density and electron density. You got 4 sites. So keeping them as far apart as from each other as possible, it's SP3. Okay? But what about this O? So what you have to do is say, well, if it becomes SP2 hybridized, will it make it aromatic? That's the question that you're basically asking. So if it becomes SP2 hybridized, you will have a p orbital on that O. What will be in that p orbital? 2 electrons. One of the pairs, okay, will be in there. Only one pair. Where will that pair be? In an SP2 orbital. Okay? All right, so what is our number going to be? 6.
So it is aromatic.
6 pi electrons, which is 3 pairs, which is odd. So it is aromatic. I'll move.
Why did the SP2 on the other one not count, but in this one it counts?
Because this nitrogen has 1 electron in a p orbital already. So the other pair can't be in a p orbital. It's in the sp2. Okay? You see the distinction? It's just a little distinction, okay? Remember, don't count 3. You're going to count 1 or 2 or 0 for anything. Okay? You're going to count 1, 2, or 0. So when do you count 0? When it's positive. Are you positive? Okay, now look at this one. Let's see how you do on that. I get watering to be the band. We're going to get all the answers again. So these will be some of your multiple choice questions. So if you go over the old test, look for things like that.
Is that our same as the week after?
Yeah. Yeah, we have next week. Then after that, we have the test.
They would have 2
Yeah. That's right, the material gets. Yeah. The last test is the first Wednesday of May. That's the last test. All right, you ready? Let's see what you did. It's aromatic. Yay. Okay, so tell me how you did it. You're locked. Is that what you're doing? No.
Yeah.
All right, so we're going to go around and count. 1, 2, 3, 4, 5, 6, 7, 8. Okay, what do we do about the nitrogen?
There's the 12 pairs.
There's a lone pair up here, isn't there? Okay. If this was an irregular molecule, that nitrogen would be sp3 hybridized. So what we have to do is go, if it's sp2 hybridized, will it make it aromatic? So we're going to go sp2. That will put that lone pair in a p orbital. Now we have 10 pi electrons. Is that an odd number of pairs? Yes, it is aromatic. And notice that the whole system, everything is sp2 hybrid. Okay? And that brings up another point that I wanted to show you today. Sometimes compounds like this get drawn like that. Okay, have you seen that?
Yeah.
Like if you probably had to look up benzoic acid and some things. Okay, that little circle means all those bonds are equivalent. They're basically the same length, and the thing is aromatic. Okay, when you do mechanisms, then what we do though is we write out the double, single, double. But if you were just writing out the molecule, you might put the circles in. So benzene, remember, had these two keculaes. But when we actually measured benzene, all of the bonds were the same length in between the single and the double. Okay? If you were to draw the resonance arrows to go from one to the other, and it doesn't matter if you make them clockwise or counterclockwise, it's all the same. Notice that if you draw the hybrid, what happens? So here's my backbone. Okay, so I'm going to have partial bonds all the way around. Look at what that looks like. A little circle in the middle. Okay, so you might find it easier to write some of the stuff as we go forward with the circle in the middle. Okay. Okay, so when you're doing benzene nomenclature, benzene itself is considered a parent or a base name and will come last in the name. With one substituent, no number is necessary. So do you agree that this compound and this compound are the same thing? It's just turned, right? We're beyond that now. Okay, so what is the name of this? Bromobenzene. Okay, benzene is your base name, and you said bromo. Okay, what do you think that one is? What? What is the group on there?
Tert-butyl?
Yeah, so it's tert-butylbenzene. Okay, this group up here is a nitro group, and NO2, those are going to start showing up now, benzene stuff. And nitro groups, that would be called nitrobenzene. Okay, that's one substituent. Okay, pretty straightforward. Chlorobenzene, I bet you already know what that looks like. Chlorobenzene. Benzene with a chlorine in place of one of the hydrogens. Yeah. Okay, some benzene derivatives have been known by common names for so long that these names have been accepted into the IUPAC system. Okay, so you look at this compound here and you want to go methylbenzene. But you know what? We don't call it that. It is called toluene. Did you use toluene?
Yeah.
Yeah, didn't you?
Dye.
What? I don't know, but I was thinking you used it in the Diels-Alder lab as a solvent. I wrote most of those labs. That's what I remembered. And you pipetted it in a little bit. Look for the charge strength for confluence. All right, look at this one. What is that group up there? You remember? It's an isopropyl. Okay, isopropyl benzene called cumene. Cumene. I have no idea how they came up with those names. Okay, this looks like methoxybenzene, but it is called anisole. Anisole. Okay, the only thing to do is memorize them. All right. What's that one? Anybody know? It looks like aminobenzene. It's aniline. Okay, now you should know this one because we talked about it. Yeah, phenol. Okay, do you know this one? You used it in lab. Yeah, ring a bell to anybody looking at that structure. No, that's okay. Styrene.
That's when we did the fun lab with.
Yeah.
Is that what you used to make the balances on?
Remember the last time?
No, the styrene was used to make the hard stuff in the test tube. Okay. Did you keep your chuck?
Mine is. I used too much
Styrene?
food.
You have hard styrene?
I used too much food.
Now,
Oh, but this was the one in the test tube. We didn't put food coloring in it. Because that messes it up. I already knew that. All right, what about this one? Do you know what a CN is? It's C. Yeah, it's like cyanide. This is called benzonitrile. Benzonitrile. Now remember, these are common names. Okay, you're just going to have to memorize them. There's no rhyme or reason for most of them. But this one is easy. What's that one? You've used that in lab, I think. Benzoic acid, didn't you use that in lab? Okay. How about this one? This one is in almond. It smells like almonds. Benzaldehyde. So you see how you get benzoic acid, benzaldehyde. Okay, and another weird one that we're going to use in the benzene area is the SO. That is benzene sulfonic acid. You know what the SO3 looks like? Okay. It still didn't take me. Quick. Okay. Remember that S will break the octet rule? It's the bane of all chemistry students. SO3H. That's what it looks like. Okay, how are we doing? We're doing good. All right, how would you name that? You remember? We talked about it already. Benzene is not the base. Yes, because this is going to be your base. Because it's way more complicated. Okay, do you remember what the benzene is called when it's phenyl? It's a phenyl group. YL, not OL, because OL is when you have an OH on there, okay? I'm telling you, you misspell something, turn it into something else. Okay, it's an octane, 3,5-dimethyl 6-phenyl octane. How come we numbered it from right to left and not left to right? Yes. Phenyl has there's no reason to give it the lower number. Okay, that's the purple root. This is the red root. So you come to something on carbon 3 and you go, okay, this is a methyl, this is a phenyl, which comes first alphabetically? Methyl comes first, so that's how come we number the red root. This is the one that wins. Okay, so you remember those little rules? Okay, what about this one? When the alkyl chain is more complicated or contains the functional group, the benzene ring is named as a substituent. It is called a phenyl group. You will also see it written as pH, like that, capital P, little h, or C6H5. That is a shorthand for the benzene ring. Notice how many carbons we have. 1, 2, 3, 4, 5, 6. And how many hydrogens? 1, 2, 3, 4, 5. Is there a hydrogen on this carbon right here? No. It's bonded to other things. Okay? And then other possibilities are a benzyl group. A benzyl group is when you have that CH2 in between. Okay? So if this had been a CH2 pH, the numbering would have been flipped. Right? Because B comes before M, and it would have been called a benzyl group. Do you want me to write it? All right, let's see. 3,5-dimethyl. Okay. I gotta remember what it is. Okay. 1, 2, 3, 4, 5, 6, 8. Okay. So see, the name of this is going to be, we can go the purple route. Okay. Or we can go the red route. Either way, we come to a substituent on carbon number 3. Okay. So who wins? Well, this is called a benzyl group. It has that benzylic carbon. Remember, that's next to a benzene ring. Okay? This is called a methyl group. Now, which comes first alphabetically? This one does. So the purple group wins in this case. So what is the whole name? 3-benzyl. And then what?
4,6-dimethyl.
Mm-hmm. Mm-hmm. Oh, my L got kind of wild. Happens when you write fast on that thing. Okay. Kind of help you remember those rules too. Remember to pick the longest chain. Remember to pick the longest chain with the most substituents. Those old rules. Okay. Okay. The common name for benzyl alcohol has this structure. Notice how come it's called benzyl alcohol. Okay, but I want you to tell me, what is the IUPAC name for that? What do you think? Okay, probably what?
Probably a fin or something in there.
Okay, so this would be a phenyl. Sigh. And then what do we got up here, you guys? What's that? What if that wasn't there? What if the benzene ring wasn't there and you just had a CH3? Well, All right, so what is it called? Methyl. Okay? Notice that this was your base because it had the functional group. Okay. Don't worry, we're not gonna do this. We're not gonna go there. Okay, that does exist, but you could do a whole class of nothing but no. I think you could kind of scatterbrain by then, but okay. So name that.
Have you done from Star Wars?
I know. Who knows?
I didn't consistency.
Who knows what I was thinking of? I thought of a weird name, and that's why I put it probably. All right, so we all got it? Yeah, nitrobenzene. All right. Okay, start learning those names. We're going to use them on Monday.